Okay, periodic trends. Terms to know. Valence electrons. These are the electrons in the outermost energy level of a Bohr diagram. Inner electrons. These are all the other electrons between the valence shell and the nucleus. So if you have a Bohr diagram, then these are your valence electrons, and these are your inner electrons. Shielding is the blocking of the positive pull from the nucleus on the valence electrons by the inner electrons. So basically, you've got this big positive core at the center of your atom, and it's pulling on all the electrons. It's pulling them in. But the inner electrons are getting in between the valence electrons and the positive pull, so they're influencing how much of the positive pull can actually be felt. An ion is an atom that has gained or lost electrons and therefore now has a charge. Cation is a positively charged ion, like sodium when it loses an electron. It's now +1. But we're chemists, we're efficient, we don't write ones. Anion is a negatively charged ion. For instance, oxygen 2-. The nucleus is the positively charged dense center of the atom, and electrons are the negatively charged very light particles traveling outside of the nucleus. So you got to have your head in the game for periodic trends. This is what you're supposed to know before we go in. Okay, so the periodic table is organized in such a way that we can easily predict many characteristics of the elements by their position in the periodic table. Now, we can estimate how they're going to react or what their physical properties are based on where they are in the periodic table. The predictable pattern by which properties of elements change across or down the periodic table is called periodicity. Now, what you've got to understand too, there are exceptions to the rules. So they're general. It's a general trend. There will be some exceptions. So don't Google answers. Go with the trends that I teach you, because sometimes this for a specific atom it might not hold true. So they're general trends. There will be some exceptions. So, what are these predictable patterns? So the elements in families have similar chemical properties. They react in the same way, and this is because they have the same number of valence electrons. There are other trends that exist too. For instance, if you go down a group, so if you go down any group in the periodic table, the metallic nature of the elements increases. Properties such as conducting electricity, being solid, being grayish in color. Now this makes sense in groups 1 and 2 because they're all metals, but this also happens in the rest of them. For instance, Group 16, you've got oxygen at the top. Oxygen as an element, O2, is a colorless gas. As you go down, you're going to hit selenium. It's a semiconductor, so it has some ability for conductivity. Then, as you go further down, you're going to come to polonium. It's a gray metal, and it conducts electricity. There's also the trend that as you move left from the right-hand side of the periodic table towards the left, also you get a more metallic nature, right? So as you go down a group, you get more metallic in nature, and as you go from the right to the left, you get more metallic in nature. So we need to examine the structure of an atom and how it changes in order to understand the trends in reactivity and physical properties of the elements. These properties can be predicted by consideration of the factors outlined in this note. So we're going to look at atomic size, electron affinity, electronegativity, and ionization energy. So we're going to talk about atomic size first. So atoms are very small. They're measured in picometers, which is 10 to the negative 12 meters. So that's pretty hard to imagine, but basically 1/trillionth of a meter, or 1/1000th of a nanometer. Maybe you've heard of a nanometer. A human hair is about 100,000 nanometers. So a human hair is 1 billion times bigger than a picometer. Because an atom's size is so small, scientists measure the distance between two neighboring nuclei and then divide by 2. Therefore, it's referred to as the atomic radius. So these terms are used interchangeably. Atomic size, atomic radius. They mean the same thing. Okay, here's a graph of the radius in picometers of an atom plotted against the atomic number. So we're going basically from hydrogen. So hydrogen is over here, all the way across to xenon. So we've got period 1, period 2, period 3, period 4, and period 5. Okay, so what do we see happening here? So who's got the largest radii? The largest radii belong to this group of elements. Who's got the smallest radii? This family or group, right? So we've got alkali metals are the biggest. Noble gases are the smallest. And what happens as you go down a group? So if we look at the alkali metals, lithium's at the top, then sodium, then potassium, then rubidium, then cesium. Same trend happens for the noble gases. Here's helium. Then as you go down, you hit neon, argon, krypton, and xenon. So basically, alkali metals are the largest. Noble gases are the smallest. And then, as we go down a group, in the periodic table, the size of the radius or the size of the atoms increases. So going down a group, the size of the atoms increases. Now, going across a period, so left to right. So here, moving left to right across the first period, starting at lithium, moving across the period, second period, across the third period, across the fourth period, across the fifth period. Now you'll see little anomalies here and there, but that's what I was talking about earlier, about generally following the trends. So basically, as you move across a period, the size size of the atom decreases. So what's the reason for this trend? So going down a group, they get larger. What we're doing as we go down a group is we're adding a shell or a ring to our structure. So therefore, the valence shell moves further away from the nucleus. On top of this, there's more inner electrons each time the shell is added. So more inner electrons. And therefore, because there's more inner electrons, there's more shielding. So both of these factors add up to this following result. There's less positive pull felt. So it's not that there's less positive pull. The positive pull also started to increase, but the amount that's felt by the valence shell is going to be less. So less positive pull felt from the nucleus. Therefore, the size is bigger. Therefore, the size is bigger. Now, going left to right, we saw the opposite effect. We saw the size getting smaller. So when we go left to right, the electrons are on the same valence shell. So shielding isn't a factor. It's going to be the same for each of them. So it's the same, so it has no effect. What has changed is the number of protons and electrons added. So it's the change to the nucleus that has the biggest effect here. So the more protons you have, the greater the positive pull. And this positive pull is felt on every single electron. So as the number of protons increases, the pull also increases, and the electrons move closer to the nucleus. So therefore it gets smaller. So think about it as in terms of a tug of war. If you have 3 people on one end and you have 7 people on the other end, the 7's going to win if they're all the same size, all the same strength, because there's more of them to pull. So this is what happens to our valence shell. The more protons there are in the nucleus, the greater the pull towards the nucleus, the smaller the atom gets. Ionization energy. So this is the energy required to remove an electron from an atom or ion that's in the gas state. So it's been put into the gas state, so energy's already been added to it. It's been put in the gas state, and you end up forming a positive ion, and it always requires energy. So energy is on the left-hand side. So the first ionization is this is the ionization energy required to remove the first electron from an atom. So then you form a 1+ ion. The second ionization energy is the energy required to pull off the next electron. So now you've pulled off 2 electrons, and so on. So third ionization energy, third electron removed from an ion. Noble gas stability. Noble gases have a full outer shell, making them very stable. So all elements want to have the same configuration as the noble gases, a full outer shell. So we should see, because they're so stable, that they have a very high ionization energy. And here's the graph of ionization energy versus atomic number. So it's plotted from hydrogen to radon. So we're going in order of atomic number. And you can see the peaks are indeed the noble gases. It requires more energy to remove an electron than the other elements in the same row. So, what other trends do we notice? We notice here that as you go down the noble gases, the amount of ionization energy required decreases. And you see the same thing down here with the alkali metals. So as you go down a group, the ionization energy decreases. So what happens as we go across a period? So left to right along period 1. Left to right across period 2. Left to right across period 3. So what we notice is as we move across a period, left to right, the ionization energy increases. So, what is the explanation for as you move down, the ionization energy decreases? As you move down a group, the size of an atom, the atomic radii, increases. The size increases. Therefore, the electrons are not held as tightly and are easily removed. I use an analogy that imagine playing football and you're running with a ball and you have your arm extended while you're running. It's going to be pretty easy for the opposing team to take that football from you because it's so far out from your body. But if you tuck it in to your shoulder when you're running, then it's held tighter, you have more control over it, and it's going to be harder to remove. So this is an analogy I like to use. Periodic trend. So moving left to right, across the periodic table, the size decreased. We know that. The size got smaller. So the electrons are held more tightly, closer to the nucleus. And it's harder to remove them. So basically, the smaller the atom, the harder it is to remove an electron. And that's what ionization energy is. It's the energy required to remove an electron. So we've looked at size, atomic radius. We've also looked at the energy required to remove an electron. Now we're going to deal with electron affinity, which is the energy associated with an electron being added to an atom. So I've put here the electron is being added on the left, and I've put the energy being on the right, but it depends on which type of atom, whether energy is required or energy is released. So the types of atoms that form stable negative ions are nonmetals. The energy value in this case is negative as it's released. Some atoms do not readily accept electrons, like metals, and so energy must be added. So in this case, the energy is positive. And of course, noble gases wouldn't want electrons either, so it'll be positive. So the graph's a little bit confusing. Okay, so as you can see, the graph for electron affinity is kind of different. So you've got negative numbers and positive numbers. So you've got high negative numbers up here, indicating energy is released. They really want the electrons. Down here, you've got high positive numbers, meaning you really got to add energy in order to add an electron. So it's a little hard to see the trends on this one because you've got to get your head around that. But basically, as you move across a period, it goes up. And as you go down a group, it goes down. So as you move down a group, it becomes more positive. Becomes more positive. So it requires more energy to add an electron. As you go across a period, you get an increase in magnitude, becoming more negative. So it's easier to add an electron. Okay, so the explanations for these trends. As you go down a group, the atomic radius gets larger, so the size gets larger. So there's less control over valence electrons. It's like an A over valence electrons. Therefore, it's harder to attract and hold on to other electrons. So the larger you are, the less control you have over your own valence electrons. So therefore it's harder to even add another electron to it. Oh, there's a typo there. Going across a period. Going across a period. So the radius gets smaller, so the size gets smaller. So the nucleus has more control over its valence electrons. And it's easier, therefore, to attract and control or hold on to another electron. So the radius gets smaller, so the nucleus has more control over its valence electrons, and it's easier to attract and control or hold on to another electron from somewhere else. So overall, the elements with the highest, oh, thank you, Netflix. I do like Stranger Things. The elements with highest negative electron affinity, so they have the highest affinity for an added electron, are those with the smallest radius. So the elements with the highest negative electron affinity, so those elements with the highest affinity for an added electron are those with the smallest radius, the highest the highest ionization energy, right? It's hard to remove an electron from them as well. Therefore, they're found in the upper right-hand corner of the periodic table. Okay, so this is the last periodic trend for the regular elements. So electronegativity, it's a quantitative measure of the pull an atom has on the electrons it shares in a bond with another atom. So it's basically a relative pull an atom has on electrons that don't belong to it. So it's not that electrons have been transferred, they're in between the two atoms. So I liken this to shaking hands with somebody. Your hand represents the electrons, so there's two electrons between you. Normally, you shake hands with somebody, you're not aggressive, you're just shaking, the hands are between you. So they're equally shared. But if you pull that hand towards you, you have a greater pull on electrons. You're a little bit negative, not a lot, because the two negative electrons are closer to you, and the other person's a little bit positive because the electrons are its electrons are no longer closest to itself. So think of it in terms of a handshake. Okay, so let's take a look at the trends here. Ooh, look at that. We have some zero values. Who would not have any pull on electrons? And they've been labeled right underneath them, except this one's a little bit up. So the noble gases have an electronegativity value of 0, and that's because they don't want any electrons, right? They're not going to form bonds. So noble gases, oops, sorry about that. Noble gases electronegativity value of 0, and that's because they don't bond. And who's got the next lowest? Next lowest will be at the start of the next period. So your group 1, so group 1, your alkali metals have next lowest value. Does that make sense? Do the metals want your electrons? No, they don't. They want to get rid of their own. They don't want any more. So as we move down a group, like the halogens, like the noble gases, sorry, not noble gases, like the alkali metals, the values go down. The values decrease. And as you move across a period from left to right, generally the values increase. So who has the highest values then? So all the halogens are the highest. And who's got the highest value of all? Fluorine. Fluorine's got the highest electronegativity value of 4.0. Okay, so the explanation. So this goes along, it's a similar trend to electron affinity. So as you go down a group, atom size increases. The atom size increases, therefore the nucleuses, I don't think there's an E. The nucleus's positive pull is effectively weakened. Therefore, there's less affinity for somebody else's electrons. Or not someone, some other atoms. Electrons. And as you go across a period, Here, across a period, the size decreases. Left to right. Therefore, the nucleus has a greater effective pull on valence electrons, and therefore a greater affinity for another atom's electrons as well. So the smaller you are, the stronger the pull on somebody else's electrons. Okay, we're going to basically label this periodic table sketch with the summary of the trends. And I want to do increasing, in terms of increasing. So when we go down the periodic table, the radius increases, size increases. When we go right to left, size increases. I know we've been talking so far about going left to right, but I'm only showing the arrows for increasing. So as you go down, the size increases, and as you go right to left, size increases. As you go up the periodic table, as you go up a group, ionization energy increases, electron affinity increases, and electronegativity increases. So going up or in the opposite direction of size, so the smaller you are, the stronger these interactions. So as you go up, the size gets smaller. Ionization energy, electron affinity, electronegativity all increase. And moving left to right, opposite from the increasing size, the ionization energy, electron affinity, and electronegativity all increase. So the smaller you are, doesn't matter what type of an element, the smaller you are, the greater the ionization energy, electron affinity, and electronegativity. So this is how size affects the other properties, the other factors. So what that means is, down here, you will find the most reactive metals, right? Because they're the biggest, they give off electrons the easiest. So there's the most reactive metals, because they want to become positive. You've got the lowest ionization energy. And over here, you've got your most reactive nonmetals, because they're the smallest, so they have the highest amount of electron affinity or electronegativity, which means they want to be negative. And that's what nonmetals do. When they form ionic compounds, they become negative. So there's the place for your most reactive metal, most reactive nonmetal. Okay, so this is the very last thing we have to talk about in terms of periodic trends. And this has to do with special case of periodic trends for atomic size for ions. So these, of course, are atoms that have gained or lost electrons. So to explain this concept, you have to remember, like charges repel. So electrons will repel each other, and protons will repel each other. Therefore, even though negative electrons are being pulled towards a positive nucleus, the electrons themselves are repelling each other, pushing out to get as far away from each other as possible. The radius of a cation, remember this is a positive ion. This is a positive ion. Will always be smaller than the radius of its atoms. So when you lose electrons, you get smaller. Atoms lose electrons to create positive ions. When the electrons are lost, there's now less electron-electron repulsion, pushing the radius out, so they get smaller. When comparing different atoms, the more electrons you lose, the smaller you get. So if we look at lithium, lithium loses 1 electron. So it forms a 1+ ion. This is about 90 picometers, where its atom is about 130. So it definitely got smaller. So this was the atom, 130 picometers. Now the beryllium, 2+ ion, it should be smaller than its atom. Its atom was about 90 picometers. And its ion, 2+ ion, is 59 picometers. So it did get smaller, but you can see that losing 2 electrons makes you smaller than an atom or an ion that only lost 1 electron. So the more electrons you lose, the smaller you get. So you'll see a trend going across a periodic table. So across a row, the next positive ion will get smaller, going left to right. The radius of an anion, or a negative ion, will get bigger. So it will always be bigger than its atom. Atoms gain electrons to become negative, so now there's more electrons than protons, right? And there's more electrons in that valence shell. So because of that, there's greater electron-electron repulsion. So therefore the radius gets pushed out. So they get bigger because there's more electron-electron repulsion. When comparing different atoms, the more electrons you gain, the larger you get. So if we take a look, let's say at nitrogen. Nitrogen will form a 3 negative ion. So the nitride ion is about 170 picometers. Its atom was only about 70. So its atom was only about 70 picometers. So it definitely got bigger. And then it's right beside oxygen. So O2 minus. It has an ionic radius of about 140 picometers, whereas its atom was only 66 picometers. So it got larger as well. But you can see nitrogen has more added electrons than oxygen does, and its radius is larger. So I know that's a lot of information to absorb, but now that you've completed your note, read through it.